today we shall be looking into the separation of a component using the multi-stage analysis. Earlier we have learnt extensively about distillation separation. Now today's lecture will be a generalized one which can be applied to various types of separation processes. So this lecture is multi-stage single component equilibrium separation. Now in this lecture we shall be learning about various types of mass exchangers, then steady state material balances, operating lines and determination of stages for the separation. Now when we talk of the multi-stage processes, we know that there could be various types of principles of separation, and some of them we have studied already, and we have examples like distillation, absorption, adsorption. Then when we are trying to understand these multi-stage processes, the analysis involves the determination of the number of stages that is obtained by considering the mass balance and energy balance equations. This also we have learnt under distillation. So by obtaining the number of stages, what we shall be obtaining? We shall be having the design and the sizing of the specific equipment, and the phases may be contacted in different manners. Now let us see that if we talk about distillation, absorption, adsorption based separation in these natural gas systems, they involve direct contact of the two phases. And what happens that when the two phases are contacted directly, they mix with each other, and thereby the mass is exchanged, that is, some species get transferred from one phase to the other preferentially, and that is how we are able to achieve separation of the various species. And in this way what we find that the concentrations of the species in each phase, and hence the phase flow rates keep continuously changing along the column, because as the species the concentration changes, what happens? We find that the effective properties or physical properties also like density, they also change. So because of these changes, what we find that the flow rates also keep changing along with the composition all along the particular separation equipment. Now there are various modes of contact in the things. Either we can have direct contact, and direct contact is used in distillation, absorption, adsorption, stripping, etc. Whereas we can also have separation, that is indirect contact, that is through membrane separation, and about which we have learned separately. So in this particular lecture we shall be focusing on only the direct contact mass exchangers. Now there could be various flow configurations, that means how those two phases are flowing with respect to each other. So we can have counter current flow rate, we may have co-current, or we may have cross flow. This is analogous to what we learned in the heat exchangers. There also we have similar kind of flow configurations. So in the counter current, what we find, the two phases flow parallel to each other but in opposite directions, and compositions and flow rates of both the phases vary along the column. In case of co-current, the two phases again flow parallelly to each other but in the same direction, unlike the counter current processes. And in this case, like the counter current process, the compositions and the flow rates of both the phases vary along the column. In case of cross flow, the phases flow perpendicular to each other, and generally what happens, the process fluid flows one after the other, flows continuously inside the particular system, whereas the utility fluid, that is the fluid which is used as an agent to separate some components, flows in a perpendicular direction, and it is always taken as fresh fluid. That means the process fluid continuously changes its composition along the column, whereas fresh fluid is inducted into the column at different points as the agent of separation. Now depending on the kinds of fluids we have different types of processes. So here we are denoting by L and V the heavier and lighter phases. These should not be confused with liquid and vapor. So, this L represents heavier phase and V represents the lighter phase. So, let us see that if the heavier phase is liquid and the lighter phase is vapor, we can have different types of separation, and examples are distillation, absorption, stripping. So, if we have liquid and gas or liquid or vapor, we can have this kind of systems. Similarly, if we have solid and liquid system, then we can have adsorption or we can have leaching. Leaching is also used in the metallurgical processes. Then we may have solid as heavier phase and gas as a lighter phase, and this finds application in adsorption. And then we may have two types of liquids with different densities. So, one is denser liquid and another may be lighter liquid, and which are immiscible. For example, oil and water, they are two different liquids with two different densities and they are immiscible. So, they will form two phases. So, that is how we say that we can have a denser liquid and a lighter liquid which are immiscible. So, this can also affect separation, and that kind of separation is obtained in extraction. So, here we have a counter current separator. A typical configuration we see here, that here we assume that there is only one solute A which is being exchanged between the two phases L and V. And here we have shown two ends as 1 and 2. This 1 and 2 denote the bottom end and top end, or bottom terminal or top terminal of the particular column. And here we have the various types of flows involved. We find that this heavier phase is coming from the top to the bottom, while the lighter phase is going from the bottom to the top, and as they flow along this column, they are getting contacted with each other, and due to the mixing of these two phases, what is happening, the particular solute A is getting exchanged between the two phases, and at some any intermediate position we are giving some arbitrary compositions x y. Here you can see there are various notations involved, like V2, Vs, Y2, Y, this capital Y2 and all these things. So, in this now we shall see what kind of notations we are having. This L and V are the molar phase flow rates, and these vary along the column. This has to be very clear that molar flow rates are changing along the column because of one of the phases is losing the particular solute, whereas the other phase is gaining the solute, and that is how the phase flow rates keep changing. On the other hand, we have another notation Ls and Vs. These are the molar phase flow rates on solute free basis. Solute free basis means that when we are calculating Ls and Vs, we are excluding the solute which is getting transferred. That means, if we exclude the solute which is getting transferred, assuming that other species are not getting transferred, it means that the Ls and Vs will remain constant all along the column. And why we are doing this, we shall see later, that by assuming the flow rates on a solute free basis, we are able to simplify our analysis. And then by small x and small y, we represent the mole fractions of the species A in L and V respectively, whereas by capital X and capital Y, we are representing the mole ratios of species A in L and V respectively. Now, what is mole fraction? We know that mole fraction of a component in a mixture is the number of moles of the particular component per unit number of moles in the mixture. On the other hand, the mole ratio means that it is the ratio of the moles. That means, mole ratio is always with respect to at least two components. So, that means if I say that mole ratio of component 1 with respect to component 2 is equal to the mole of component 1 divided by the mole of component 2. So, this is the mole ratio. So, in this case, if we assume that only species A is getting separated, that means we can take rest of the species as one single pseudo component. So, when we talk of the mole ratio, it would mean that the mole ratio of component A with respect to the rest of the components means the number of moles of component A divided by the number of moles of the rest of the species in the mixture. Now, this mole ratio and the mole fractions can be easily correlated, and here I have shown this relationship between the mole ratio and the mole fraction, and this can be derived very easily that this mole ratio is the number of moles of the species A and 1 minus y represents the number of moles of the rest of the species. Similarly, we have the solute free basis flow rate, and that is represented by this total flow rate divided by the 1 plus y. Okay. So, naturally we see that the solute free basis flow rate will be always less than the actual flow rate, because we are taking out one of the components from the whole flow rate. So, similarly we have the mole ratio in the L phase related with the mole fraction in the L phase, and this is the solute free flow of the L phase related to the solute free thing of the, this will be x, this is the mole ratio. So, this is how we are able to correlate the mole ratio with the mole fraction and the solute free flow rate with the total flow rate. Now, here we have to remember that x or y, that is this mole fractions, these mole fractions are between always 0 and 1, that we know, but we see that the mole ratios can vary between 0 and infinity. You can easily see that if you put y as 0, then this capital Y is 0, and if you keep y as 1, then this bottom one becomes 1 minus 1, that is 0. So, this y tends towards infinity. So, that is how we find that mole ratio can go from 0 to infinity, whereas mole fraction will stay only between 0 and 1. Here in this slide, now we go for the analysis. Now, what we do here is this, that first we locate one particular control volume which encompasses the terminal 2 and at some arbitrary height of the particular column. Here we see that ingoing streams are this vapor from the this thing and the liquid from the top. So, now if we do a steady state material balance, assuming that the two phases L and V are immiscible, then we find that this is the ingoing stream, that is Vs into the capital Y is the amount of species A going in, and this Ls into x2 is the amount which is going in, and the coming out is the Vs into y2 and the Ls into x. So, this is how we are writing the whatever is going in is equal to whatever is coming out at steady state. There is no accumulation. Now, of course, you please understand that we can also put this thing in terms of the mole fractions. If we put in terms of mole fractions, then we have to use the total flow rate. Now, because Ls and Vs are constant, and then we can rearrange this equation, we find that this is the mole ratio in the V phase and these are the mole ratio in the L phase, and this is the terminal mole ratio in the V phase. And because Ls and Vs are constant, so this particular Ls by Vs is also a constant. So, the slope is a constant. So, we deduce that this is an operating line equation because this correlates at any given height, it correlates the compositions of the L phase and V phase. So, this is operating line is a straight line with the slope of Ls by Vs and the y intercept is y2 and it passes through x2 and y2. That means, if you put x equal to x2, then we will find y equal to y2. So, this is the straight line operating line equation for this particular column. Now, what we do? We look at the column as a whole. Now, here we choose another control volume 2, which is encompassing the whole height of the column, and now when we write again the steady state mass balance over here, we find we have this Vs into y1 plus Ls into x2, that means Vs into y1 plus Ls into x2 is equal to Vs into y2 plus Ls into x1. So, that is how we are writing the steady state mass balance for this control volume, and again rearranging this we are getting this particular equation. Now, what we find here that x1 and y1, okay, that means this x1 y1 they also satisfy the operating line equation, that is this equation is also satisfied by x1 and y1, and this that means the operating line passes through both x1 y1 and x2 y2. That means the operating line will connect both the terminal concentrations of the two species in the two phases. Now, let us see that how to graphically represent this kind of a system. Now, we need both the equilibrium curve and the operating lines, and we understand that the equilibrium relationship may be nonlinear in terms of mole fraction, but when we represent in terms of the mole ratios, that may come as linear. Similarly, if we have the equilibrium relationship in terms of mole fraction as linear, that in terms of mole ratios it may turn out to be a nonlinear. Now, let us assume for the time being that we have a linear equilibrium curve without loss of generality. So, we find that this is the way we are at any given stage, this n represents a stage. So, at any given stage we are this equilibrium relationship between yn and the xn, this is given by this equation, and this alpha is the equilibrium constant or the distribution coefficient. Now, once we have done this, now what we find that if we now try to plot it, now here we find that on the x axis we are plotting the mole ratio in the L phase, on the y axis we are plotting the mole ratio in the y phase, and it's both of them start from 0, and you can see that we have not put any kind of number at the other end of the particular curve, because unlike the mole fractions, these mole ratios can go to any number. Okay. Now, first what we do, we put this particular line is the equilibrium curve, and then we can have different types of the operating lines depending on what is the direction of the species transfer. Now, here we have one operating line which is also passing through x1 y1 and x2 y2, and this is the operating line we shall be obtaining if the species transfer is taking place from phase V to phase L. This you can see very easily. On the other hand, if the species is getting transferred from phase L to phase V, then we find the operating line will be below the equilibrium curve, and on this operating line also we can locate the point x1 y1 and x2 y2. Now, please understand that this x1, when the species is coming from V to L, x1 y1 will always be more than x2 y2. That you can see easily from this particular graph, that if the thing is coming from V to L means this particular V phase is getting enriched with the getting depleted by the particular solute, and this L phase is getting the solute. So, what is happening? This x1 is going to be more than x2, but on the other hand, if it goes the other way down, then what we will find that the V phase will get enriched, whether L phase will get depleted. So, that is why we find the locations of x1 y1 and x2 y2 also varies in the particular curve. So, here we find x1 y1 is more than x2 y2, whereas in case of L to V we find that x2 y2 will be here and x1 y1 will be on this side. Once we have known this, now what we do that as we have done in case of binary distillation column analysis, we can also make some kind of staircase construction. This I shall not explain, you can refer back to the lecture on the binary distillation, and here we simply do that, assuming that the transfer is from V to L. What we do that here first we draw again the equilibrium curve, and then we draw the this operating line. Then what we do let's suppose we start from the x1 y1 and we drop down to this equilibrium curve, okay, and then we keep on doing the staircase to go to the next level, and similarly we keep on moving this way, and then what we do, wherever we are crossing this particular given composition, we shall be taking this small fraction. That means out of this whole equilibrium stage, we shall be considering only the small fraction over here. So, this is also the same thing we did for the binary phase distillation column separation using the McCabe-Thiele method. So, in a similar fashion, what we do that we count the number of equilibrium or ideal stages as whichever is connecting the operating line with this particular thing. So, this is counted as 1, 2, 3 and so on and so forth. So, this is exactly the same whatever we have learned under the McCabe-Thiele method. So, this is now we are finding the number of equilibrium stages. Now, there is another way of finding the algebraically the number of ideal stages, and without any derivation I shall give you the final form of these equations, and these have been derived by Kremser, and this is known as Kremser's equation or sometimes Kremser-Brown-Suders equation. So, these equations are giving us the ideal number of stages, and here we find if the transferred is from V phase to L phase. So, this is the particular expression, this is used for finding the number of ideal stages. On the other hand, if the transfer is from phase L to phase V, then this is the equation which is used for finding the number of ideal stages. In these two equations, we have another parameter, that is A over bar, and this A over bar is the absorption factor and defined as Ls by alpha Vs, and this 1 by A over bar, that is the inverse of the reciprocal of the absorption factor, is called the stripping factor, sometimes denoted by S over bar. So, in terms of this absorption factor, stripping factor, we are able to express the number of ideal stages algebraically. Now, if we find that the absorption factor varies along the column from top to bottom drastically, then what we need to do, that we shall be taking some kind of average, and it is generally a geometric average is taken between the absorption factor at the top and at the bottom, and here we are finding that 1 is representing stage 1 and n representing stage n. So, this Aj, at that means if j is between 1 or n, Aj will be Lj by alpha Vj. So, in this case we are assuming that alpha may be constant or it may not be constant, it may be also varying from stage to stage. So, this is how we are finding the algebraically the number of theoretical stages. Now, to know more about this, you can refer to these two books on the mass transfer. Thank you.